We are in our last unit. That is super exciting, right? Thank you.
Bro, what about
I'm so hyped.
I've never defended anything passionately in that class.
I can't wait to review, because then I'll go
you
back
know,
and I'll
you should
understand.
just get rid of titles like that, and I'm like, no, we shouldn't. Fight first.
Alright.
I'll understand.
You're
it.
We are going to understand it all.
I'm not sure what I'm saying.
You what?
So what we're going to be doing today and tomorrow is talking about cross sections. So there's basically two more big topics that we have to talk about. One of them is cross sections, and one of them is revolving. All right, that's what Unit 12 is about. So today we're doing cross sections, and we're doing cross sections with squares and rectangles. So the volume of the cross section is known as the integral from a to b of a of x dx, where a of x is going to be the area. So you might say, like, this looks like just a regular integral, and it is kind of, but the formula on the inside is the area of the cross sections. All right, so like I said, today we're going to be doing rectangles and squares. Now, what is the area of a rectangle? Length times width. And the area of a square?
Side squared.
Side squared, s squared. So those are kind of the two area formulas that we are going to be doing today. So I do have some visuals because these are really, they're hard to see at first. So I do have some visuals to show you, and I have a model over here that I'll pass around here in a second, but I want to read the question so you know what this is pertaining to. A region is bounded by y equals x squared and the square root of x. So if you look over here on my graph, this guy is which function?
X squared.
X squared. And then we have this guy here, which is?
Whatever the other one is.
Yep, square root of x, the other one. And the region bounded by these two curves is the base of my solid. So the region getting bounded, this guy right here, is the base of my solid. And my solid is going to be formed by taking cross sections perpendicular to the x-axis that are squares. And I want to find the volume of this solid. So if you were to try to draw this, which I do not recommend, I'm going to show you kind of three-dimensionally what it looks like, but if you're trying to draw this, you're going to take this length right here. That is going to be the length of a square. And so your square is going to go like this. Now if you look, this length right here is not quite as big, so your square isn't going to be quite as tall. And as you get closer, this one's even shorter. And if you imagine these squares being taken infinitely, it is going to form some three-dimensional shape. Now, it is kind of hard to visualize 2D, especially with my kind of shaky drawings of a square. So let me show you what I'm talking about here. Here we go. Okay. Same equation, we have the square root, we have x squared. I have squares checked off because we're going to do squares today. So if you...
Say triangles.
We're doing triangles tomorrow.
That's
Oh, I'm going to mess this up. Just go back. Just go back. Okay. Why are you thinking so hard now? I just tested you last period.
that's unfortunate. Lesson's over.
No, I guess we can't do it.
There we go. Okay. All right, so here's my shape. So I've got the square root function and I've got the x squared function, and I'm going to do squares because we're doing squares today. And so if you were to draw 20 different squares, they'd all be these different lengths. Does that make sense? And then you're going to take this number and you're going to draw infinitely many squares, and so it's going to take up the entire area. So what this looks like, three-dimensionally. Okay, why are you not turning? I want to see it 3D. There we go. Okay, so can you kind of see the 3D shape that's forming? And if I go more and more and more and more and more, do you see it?
Oh, yeah.
So this is like just like a couple squares.
It's also easier to see like that, yeah.
Yeah, so those are like just a couple squares, and then if you're aware of it, like when you do the integral, you take infinite, and so the more you get, and it becomes this actual three-dimensional figure. Do you kind of see it?
Can we see what the triangle look like?
So a triangle would be like pokey on top,
So shorter.
kind of like a fin. Yes, a fin.
It's a fin.
Fin, F-I-N,
Fin.
like a shark fin.
Fin, that's not more sense.
Nice.
Or like,
This one has like 2 points at the top because of the square. You gonna see it? And then a semicircle would be like a dome.
It looks like something on the plane.
Back of the plane?
Yeah.
What's on what?
All right, so if that is too hard for you to visualize,
It's not the whole tail, Tom. It's like the little thing on top of it.
I also have a model that I made. So you can actually hold it and touch it and look at it three-dimensionally. Obviously this model, because I've used little foam pieces, it's not to infinity, but you can still kind of get the idea and the three-dimensional shape that was made. And I made this, I can't remember when I made this, but I had intentions of doing like different shapes. But after doing 2 of them, I got really tired of doing it. So I only have 2 models, but maybe later on I will have more. So the difference of these 2 models though, is that one of them is in terms of x perpendicular to the x-axis, where this guy right here is perpendicular to the y-axis. So do you see how my squares are going this way?
Instead of,
Yeah.
And then on that one, they're going to go this way. They will give you different shapes. So it does matter if you are in terms of x or in terms of y. So that's kind of the 2 differences between these guys. But they do make kind of similar shapes. They will not be the same area if you are in terms of x or in terms of y. That could, not the same area, the same volume. It could affect the volume of your shape. But visually, do you kind of see what we're finding? We're doing squares and rectangles today. But that is kind of the idea. The idea.
I was just gonna throw it.
You're not pro. I don't know how strong this is.
They're pretty strong. I like covered them in glue so they wouldn't come apart.
No, it's not.
It looks the same.
No.
Yeah.
No. Hey.
It's not. It's slightly the same. Hey, Easton, let me see that one.
Okay.
It can't, right? It literally cannot be. From this side it is.
Look,
They kind of.
this one goes like this. And that one goes like
I
this.
started to do a flip. I'm not doing it.
The shape is the same.
Yeah,
Oh.
this one, the shape
Oh,
would
hey.
Oh,
be.
it's a little bit faster.
It's, yeah, it's like
Little guy?
it's not
Yeah.
quite the exact same. Even if you turned it this way, it still wouldn't be the same thing. You know what I mean? So it's a little bit different, but it's also very similar.
That was not work.
He's closer. Yeah, I'm pretty close.
Oh, you got 2 of them.
Yeah.
All right. Anyways,
You actually don't even know what a fin is, bro.
let's do these notes.
Gosh dang it, bro.
So on example 1, we have a region is bounded by x squared and the square root of x. It forms the base of a solid. For this solid, the cross sections are perpendicular to the x-axis, and they are a square. What is the volume of the solid? So there are 2 important things that you are looking for on these questions. The first thing is, what are you perpendicular to? Because that is going to tell you if you are in terms of x or in terms of y. So because we are perpendicular to the x-axis, I know that my whole function is going to be in terms of x. Your bounds need to be x, your function needs to be x, your ending will be dx. The other thing that is important is the shape you have. I have cross sections that are squares. So all of my little shapes should be a square, and that is the area formula that I'm going to use. So my first step is to figure out the area formula. The area of a square is side squared. Now, like I said before, I am not actually going to draw the little squares on my picture over here because it gets looking weird when you try to draw 3-dimensionally with the cross sections. Instead, I'm going to just draw a line, and I'm going to make it perpendicular with the x-axis so I can see the top and I can see the bottom, because that is what's going to tell me the length of my side. So the length of my side is going to be the top function minus the bottom function. Very similar of how you did the area, because if I take this whole length here and I subtract away this length, that's going to give me the length of my side. So you do the pink function minus the blue function. Alright, so pink function is square root of x minus the blue function is x squared, and all of that is being squared because of the area formula. The area is side squared. So this guy right here represents the side, the squared represents the area of the square. Length times width. Is that okay? Alright, so the squared here is coming from the squared there. Once you have your area formula, now we are going to write the integral, because remember we are adding up all of the infinitely number of squares in this shape. So we are going to integrate from what to what?
0 to infinity?
0 to 1, because it's just going to be the bounded area.
Oh.
So 0 and then to 1. We want x values because we're in terms of x. So 0 to 1 because that's how far my shape goes. And then we are going to take my area equation and put it in the integral. Square root of x minus x squared dx. And then type that in your calculator and it gives you 0.1285. Does that make sense? Okay. So on example 2 here, oh, it says same as number 29. That's supposed to say, I forgot to change that. That's what it says. Same as number 1. Same exact question, except now we're going to be perpendicular to the y-axis. All right, so I'm going to show you how it's a little different. We are perpendicular to the y-axis now, so everything is going to be in terms of y. We are still taking square cross sections though. So my area is still going to be s squared. When I'm looking at my functions, the pink function right here, which originally was y equals the square root of x, is going to turn into x equals what?
X squared minus
Y squared.
Oh, wait, she's not right. That worked out right.
And then the x squared function,
X
So-
equals square root of y.
yeah, so y equals x squared is going to be x equals the square root of y. Technically plus minus, but because I'm using the right side, I just need to do the plus square root. Because this over here would be the negative plus u, square root. Does that make sense so far?
Yep.
We good? Okay. So now I have my functions in terms of y, which is what I need because we are going to be in terms of y. Everything will be y. Bounds will be y. Functions will be y. We will end with a dy. All right, so I need to write my area function. I'm going to draw my little line perpendicular to the y-axis so I can see what the side is going to be represented by. All right, so what is the right function?
What? Square root of y.
Square root of y. What is the left function?
Y squared.
Y squared, and it's being squared. So once again, what is inside here is represented by that line, and the extra squared there is from the area formula. Okay, once I have my area formula down, I can write my integral. So the integral is going to be from what to what? 0 to 1. The y numbers though. And then we are going to put my area formula in here, square root of y minus y squared dy, which is going to give you the exact same number, but only because x squared and square root of x are inverses of each other. They're intersecting at 1, 1, so the x and the y's are the same, and my shape is a square. So that is the only reason why those values are the same. Other than that, they will not be the same values. So integrating in terms of x and integrating in terms of y are important because it will give you different numbers.
Unless we had a problem with this.
Yeah, unless everything is like inverse or the same. But that's rare, you probably won't get that. All right, let's look at number 3. So I've got a base of the solid, it's bounded by x cubed, y equals 0, and x equals 2. So I've got this little shape right here. So this curve is which function? We'll was a bad highlighter job. That's a little bit better. What curve is that? X cubed. And then I've got this one here, which is x equals 2. And we are bounded also by this one right here, which is y equals 0. Alright, so it gives me that little shaded area that I have. Now on letter A, it says find the volume of the cross sections taken perpendicular to the x-axis. So are we in terms of x or in terms of y?
X.
Terms of x. And what kind of shape do I have?
Rectangle.
I've got a rectangle. Alright, so I know I'm going to be in terms of x, and I've got a rectangle. What is the area of a rectangle?
Length times width.
Length times width. I'm going to use height times width just because that's what they use. Because they're telling me stuff about the height and the width. Now, no matter what, if you have an area equation, it has to be in terms of one variable. So before you even start messing with your graph, get this area equation so it has one variable, because otherwise you can't do anything. So what else do I know about this that's going to help me write this in terms of one variable?
The height is double the width, so it's 2W.
Yes. So the height is 2 times the width. So in place of h, I'm going to put 2w. And what is 2w times w?
3W. Or sorry, 2W squared.
Yeah. And now I have my area equation. It is in terms of one variable, which is w, which is fine. We don't really care what the variable is as long as it's one variable. All right, so now I'm like, okay, I got my one variable. Now I'm going to come back over here to my graph. I know I'm perpendicular to the x-axis, so it needs to go vertical. All right, so what are my bounds going to be?
From negative, or was that 0?
0 to 2, x bounds, because everything's in terms of x. 2 parentheses, what is the w going to be? What is the, oh, I guess I wrote that earlier. All right, we'll do it this way, that's fine. What's the top function?
X cubed.
X cubed. What's the bottom function?
0.
0. And then squared. So this guy here was x cubed minus 0. Because it's top minus bottom. Does that make sense? And then dx. Do you really need the minus 0? No. Is that okay where I went from there?
No.
Are you confused about this part? The x cubed minus 0?
Yeah, because what if the,
So the top function, or the top part of my line that I drew
so you
is,
don't worry about the green.
nope, that's my bounds. Because that's what I'm going from 0 to 2. So that's why the green matters, is because that's where I'm stopping my border. And so the only thing that matters in the area equation is top minus bottom, which is why I like drawing this line right here, because then I'm just looking at the line and I'm like, what's hitting the top, what's hitting the bottom.
Okay. Then yeah, we're good.
And then you type that in, or you work it out by hand. We don't have space to work it out here, so I'm just gonna tell you it is 36.571. I will say, especially in this unit here, once we get to the end here in calculus, a lot of the questions are set up but don't solve. If they are solving, which I'm gonna do one solving question today, where I'm gonna work it out all the way through, their stuff will end up canceling and it'll be nicer. But if you get something icky, it's not really meant to solve by hand. All right, so let's look at part B. It says find the volume of the cross section taking perpendicular to the y-axis. So now we are in terms of y. And we have a new shape. It's still a rectangle, but the information it gives me about the rectangle is different. So my area of a rectangle is still height times width, but what does it tell me that I can plug in to write this in terms of one variable?
6.
6 is the height. So my area equation is going to be 6w. Not squared, just 6w, because the height the whole time is going to stay 6. Does that make sense?
Yep.
Okay, so now let's go over here and look at my shape. So I'm gonna erase this other stuff here. Now what do I have to do to my functions since I'm in terms of y?
I'll flip that, so.
So on this one here, that was y equals x squared. How can I rewrite it?
Cube root of x.
Cube.
Cube root of y.
Cube root of y. And then this one can still stay as x equals 2, and this one can still stay as y equals 0. That's not going to matter. Okay. So now for my line here that I'm going to draw it perpendicular to the y-axis. So we're thinking right and left. The 6 is going to stay on the outside. What is the right function?
2.
2. Your right dot is at 2. Where is your left dot at?
Cube root of y.
Cube root of y. And so then this is my area function. The 6 is out there from the equation, and then the w, which is your width, is going to be 2 minus the cube root of y. Once you get your area equation, we can plug it into my integral. What are my integral bounds?
0 to 8.
0 to 8, because they have to be y. So 0 to 8. And then 6, 2 minus cube root of y dy, which I think is going to give you 24. Okay, how are we doing so far? Good? We only have one more. This is the one we're going to work out from start to finish. And if you notice, this one doesn't give you a graph. So example 4 says find the volume of the solid whose base is the region bounded by the graph square root of x and x equals 5. The cross sections perpendicular to the x-axis are squares. So a couple things that I'm making note of here. Perpendicular to the x-axis means you're going to be in terms of what?
X.
X. And we are squares. So what is the formula for square?
S squared.
S squared. Which squares are nice because you're already in terms of one variable. We just need to figure out what S is. We need to figure out what top and bottom are. All right, so I'm going to draw a graph. What does the square root function look like?
Just a little.
Yeah.
Line.
And what will x equal 5 look like?
It'll be a straight.
Yeah. Up and down line, x equals 5. All right, so when I draw this, you should notice the little region here forming, and that's the base of my solid. So the base is where you're going to draw your line, and we are going to draw it, oops, I'm not going to use, from the top all the way to the bottom, perpendicular to the x-axis. And then I can visually look at this line and be like, okay, what is the top of this line? What is the bottom of this line? And that will tell you top minus bottom. So for my area equation, what is the top going to be?
Square root of x.
Square root of x. What's the bottom going to be?
0.
0. Do you really need the 0? No. So this is just the square root of x squared. So anytime you hit the axis, whether it be x or y, that's 0. Does that make sense? Okay. Now what is the square root of x squared?
X.
X. And so x is my area, right? We've simplified area all the way down to just be x. So when you are integrating, we are going to integrate from what to what?
0 to 5.
0 to 5. And then my area formula is just x. What's the integral of x?
X squared over 2.
And my bounds are going to be from 0 to 5. Which one do you plug in first? So you get
25 halves.
25 halves minus
0.
0, which you don't really need. So your answer is just 25 over 2. So a lot of times if you have to actually work it out and integrate, like it's a multiple choice and your answers are regular numbers, it's going to be something more along the lines of that. Not something super nasty that you're going to have to like FOIL or do all kinds of stuff with. It'll be something where like your square root of your square will cancel and then you're going to integrate the terms left over. All right, does that make sense?
Yes, ma'am.
Okay, so that's it for the notes. You do have a homework in the back, or not in the back, but I passed it out to you. It's only one page, and so is tomorrow's. I'm trying to make it one page. You're going to have a homework quiz tomorrow, and tomorrow we're doing triangles and semicircles. So very similar, just some different shapes. What's up?
Can we get our homework with this?
Are you not going to be here tomorrow?
No,
Oh, the the ones you're missing. Yes, let me talk about flashcards and then I'll get your homework quizzes. So, I finally got my flashcards done. This is basically what we're gonna do. We're not gonna do them all at once. We're gonna do them in phases. So I've got the light yellow, which your colors don't have to be the same as mine, but this is why I wanted them to be different colors because I'm gonna give you groups at once. So like the light yellow ones here that I have, they're my integral function. So if I tell you to get your integral ones out, we can just get these out. And then I have my application of derivatives where it's like speeding up, slowing down, increasing, decreasing concavity, all of those things. And then I have limits, and then I have theorems, and then I have geometry, which I actually have for you today. So these are your geometry ones: area of equilateral triangle, rectangle, square, semicircle, all the things that you hopefully already know, but we're gonna review just in case. And then you have differentials, which I did in white, and derivatives, which is the heavy one, that's in purple. So if you're like, I don't have that many color of note cards, well, you're in luck because I did buy note cards, but I'm not totally sure I have enough of all of it, but I'm really, really close. I think I'll have enough. But you are welcome to use my note cards. I bought them for you, so don't be shy. I don't have white ones, though. You can go buy yourself white ones. But I've got these colors. All right, so you're welcome to use mine. What you're gonna do is you are going to cut these up, put them on one side, cut the answers up, put them on the other. Does that make sense? So these are all one color. If you want to start, you can. All right, I cut the edges off. So all you have to do is like cut them up and then put them where they go. If you are questioning which one goes with which, let me know because they're not actually in order. They kind of are in order. They go, yeah. They go like if you have this one and you have this one, they go like this. Does that make sense? But I don't want you to tape them together. I want you to tape them on a colored note card. But that's how the
Oh, is
order
that all
works.
in there?
Do you want
No, I don't need that for Q's. All right, so are y'all good on the note cards?
Yep.
Good on the homework? Y'all need homework quizzes? You're welcome to come grab them now. I guess there's glue in the back. I have like regular glue. I think I ran out of glue sticks. So, anywho.
Do you care if we just tape them or you want us to?
No, you can tape them if you want. So that's the goal for this unit here. We're gonna do, because that's what this lesson is over. That's what you need for it, is all of the geometry formulas.
What is it? These are the geometry formulas?